Hi, I'm Scott Knockleby. In this video, we're going to look at singularities of robot manipulators. By the end of this video, you should be able to explain what are kinematic singularities and their impact on robot manipulators. As well, you should be able to find the singular configurations for a robot manipulator. So we previously saw for the forward velocity solution that the velocity of our end effector is equal to this matrix J, the Jacobian, times our vector of joint rates Q dot. Now, the inverse problem is we can just simply multiply both sides of this equation by J inverse, and we can find then, given a desired velocity of our end effector, what are the required joint rates. Now, this equation here is only valid if our Jacobian is square. So let's make a note. This assumes that J is square. So in the case of a spatial robot, it'd be a 6x6 matrix. All right, as well, it assumes that J is non-singular. Okay, so as long as we're not in a this is non-singular, our Jacobian, and it's a square matrix, we can use this for our inverse velocity solution. But what happens if J is singular? All right, so when the Jacobian becomes singular, all right, this occurs at certain configurations Q. So given certain joint angles and joint lengths, if it's a prismatic joint, they can create configurations where our Jacobian is singular. All right, and we call those Q values the singularities of our manipulator. Sometimes they're also called velocity degeneracies, all right, because we actually lose a degree of freedom. So why do we care about singularities? Well, it becomes important when we're trying to determine joint velocities Q dot, such that the robot moves with a certain velocity in Cartesian space. So if we're trying to move our robot arm, say in a straight line in Cartesian space, all right, we use our inverse displacement solution to figure out the joint angles we require. All right, we use our equation here to figure out what joint rates require to move the end effector at the desired speed. All right, and then if we start approaching a singular configuration, all right, we can actually get infeasibly high joint rates. So as we use our equation here, Q dot is equal to J inverse times V. As we near singularity, our joint rates can get higher and higher, all right, until they can actually become unfeasibly high for our robot. All right, and typically a robot would just shut down. It would just say, I can't achieve that velocity anymore, and it will shut down. If we were able to actually get right to the singularity, it would require infinite joint rates, which obviously is impossible. And at that singularity, the robot instantaneously loses a motion degree of freedom. All right, so if we were a 6 degree of freedom robot, we hit a singularity, we'd be down to 5 degrees of freedom or even less, because you can have multiple degrees of freedom loss in singular configurations. So it's important that we know what these singular configurations are, so when we do our path planning, we can try and avoid them. So where do they occur? Singularities can occur when the end effector is near or at the boundary of the workspace. All right, so if the robot arm is stretched out, it can't command a velocity any further outwards. All right, and so that would be a singular configuration. All right, but they can also occur inside the workspace. And this happens typically, for example, when two or more joint axes line up. So if we were to use an example of this would be the spherical wrist. That's common on our 6 degree of freedom robots. All right, so our spherical wrist, if you recall, we have a revolute joint, perpendicular revolute joint, and then another revolute joint. All right, and so this would be, say, Z4. This would be Z5. And this would be Z6. Now, for certain values of theta 5 here, we can actually have joints 4 and 6 collinear. All right, so if we were to draw that, it would look something like this. All right, and you can see in this configuration, Z4 and Z6 are collinear. And Z5 would be here. All right, and so in this case, we now have two joint axes aligned. All right, and so we actually will lose a degree of freedom of motion. All right, so the robot loses 1 DOF because we now have two joint axes aligned. They're both achieving the same motion, so we've lost a degree of freedom instantaneously. So let's look at an example of how we find our singular configurations. We're going to use a simple RR planar robot. So we have a base pin, link 1, we have link 2, so we have L1, L2, we have our end effector point, and then we'll put the x-axes in. So here we have x0, x1, x2, and then x3. All right, so we can find the Jacobian of our end effector for this planar robot, and we're going to do it with respect to frame 3. All right, we can do it with respect to any frame, but if you were to do that, you'll see that our Jacobian is this form. All right, so to find the singular configurations, we just determine the Jacobian to 0. So we take the determinant of that matrix there. All right, and it's just simply this times this minus this times this. And then we'll get L1, L2, S2. All right, and so this equation equals 0 when S2 equals 0. All right, our lengths can't be 0, so it will occur when S2 equals 0. All right, and there's actually two possibilities when S2 is equal to 0, so that's sine of theta 2. Sine is 0 at 0 degrees and 180 degrees. So if theta 2 equals 0 degrees, all right, in that case, the manipulator is stretched right out. Okay, or when theta 2 is equal to 180 degrees, and this is when L2 is folded back on L1. All right, so the manipulator is folded completely back on itself. Okay, in either case, we've lost a degree of freedom of motion instantaneously. All right, let's look at another example. So this, we're going to look at the 3R manipulator that we've looked at in previous examples throughout these videos. Okay, and if you recall, we found our Jacobian for our end effector with respect to the base frame as such. All right, you can do the determinant of this 3 by 3 matrix, and if you were to do that, you would get, so our determinant of our Jacobian, you get L1, L2, S2 for this determinant. Okay, and so again, if S2 is equal to 0 in this case, we're in a singular configuration. So let's draw that out. So if S2 equals 0, in other words, theta 2 equals 0 degrees or 180 degrees, the manipulator is in a singular configuration. So for this robot, when S2 is equal to 0, and we'll do the straight arm case, so when theta 2 is equal to 0, it would look like this. All right, we have L1, L2, L3 in our end effector point there. And so what's happening in this configuration is we cannot move this point outwards anymore. So we cannot rotate the end effector about its center. So we've actually lost the rotation degree of freedom instantaneously in this configuration. So let's make a note of that. All right, so in this configuration, the manipulator is not capable of rotating the end effector about its center. So in other words, we've lost the orientation degree of freedom instantaneously. Okay. So singularities also have an impact on our forward force solution. So if you recall our inverse force solution, so given the desired wrench to be applied by the end effector, it was equal to the Jacobian transpose, and that would give us our torques. Now the forward force problem is given the desired torques, all right, what is the wrench applied by the robot? All right, so in this case, we have to take the inverse of the Jacobian transpose and multiply both sides in order to figure out that wrench. All right, and so we'll call this equation star. All right, so similar to the inverse velocity solution, star is only valid if the inverse of J exists. So in other words, J has to be square and non-singular. All right, so if J, the determinant of J equals 0, again, the manipulator is in a kinematic singularity. In this case, we cannot apply an arbitrary load. All right, so let's draw that out and show what we're trying to talk about there. So looking at the RR planar manipulator with S2 equals 0, all right, that's our arm is straight out. Again, this is L1, this is L2, this is our end effector. We cannot apply a force in this direction. All right, so our manipulator cannot apply a force in this direction. All right, it can't push out any further. All right, and you can look at that if you put your arm straight out. Right, you can't keep pushing a force in that direction. All right. However, although we can't apply a force in that direction, we can actually sustain a force in the opposite direction. All right, so we can sustain a force in this direction with actually no effort from our actuators, because the line of action that force passes through both joints. So in a kinematic singularity, a manipulator can sustain a force in a certain direction with no torque or force, so torque if it's a revolution joint or force if it's a prismatic joint, required from the actuators. So let's draw that out. All right, so again, we're in our singular configuration. We have L1 and L2. We have our end effector. In this case, we can sustain a force in this direction because the line of action of the force passes through both joints. All right, we actually require no torque. So let's make a note of that. No torque is necessary to sustain this force. So no torque is necessary from the actuators. All right, since the direction of the force intersects both joint axes. All right. In theory, we can sustain an infinite load, right? Because we have no torques required. In actuality, we can only sustain the mechanical strength of our joints, all right, until those joints would actually physically break. But we would require no torque from those actuators. All right, and the human body actually does this, right? So it's a lot easier to stand with your legs straight, all right? The force goes straight down your leg, so you don't need, effort from your muscles in your knees, say. Or, if you're a weightlifter and you lift a load of weights up, you want to quickly get your arm straight because there's less load than if your arm was, say, at 90 degrees. Your elbow, I mean. So it's an interesting result of these singular configurations. Although we can't apply a load this way, we can sustain the load in the opposite direction.